Okay, so I'm going to talk about the occurrence rate of exoplanets beyond the snow line as a function of host star mass, and this is kind of a precursor of much of the science that Roman is going to do. One of the reasons that Roman was selected is that we can measure the masses, use Roman data to measure the masses of a large fraction of the planets found by Roman. So how do I advance the slides here? All right, so the mass ratio function that last week I referred to, it comes from this Suzuki et al. 2017 paper. So microlensing naturally gets mass ratio function because the mass ratio is one of the model parameters. But there's a scaling with the Einstein radius, and if you don't have additional information besides, the raw light curve, it can be more difficult to determine host star masses. And so the straightforward way of analyzing a microlensing sample is to focus first on the mass ratio and then get the host masses for the events where it can be measured. Okay, so this is a plot from one of the papers from our group led by Sean Terry, and this shows mass distance curves from a number of different observations. So it's supposed to be so this is well, for those in the room anyway, this is the mass distance relation due to the measurement of the angular Einstein radius, which we can often get from light curve when we have finite source effects. And if we detect the host star, then we can measure it from the lens source separation. This is a curve from microlensing parallax, which is going to sometimes get into orbital motion. You can also get it from multiple satellites. And then when you detect the lens, we can get a mass distance relation depending on the passband. And so we like to get multiple of these relations that all converge in the same spot. That gives us confidence that the interpretation of the event is fairly simple and we understand it. All right, and so analysis we're going to present is developing the mass measurement methods to be used by Roman galactic exoplanets. Okay, so here's here's our examples of some papers from our group. So we're basically using HST and CAT and active optics to measure the lens and source stars as they separate. And we get the brightness and also measure the separation as a function of time. And this allows us to determine the masses. So here's the more events. One sort of complicated event is going to be mentioned in the next poster talk by Katie Van Dorrel. And then occasionally we don't detect the host star. In this case, we should have been able to detect the host star if it was a main sequence star. And the microlensing parallax constraints rule out both brown dwarfs and stellar remnants, except for white dwarfs. And so we believe this is the first sort of Jovian Jupiter-like planet and Jupiter-like orbit found to be orbiting a white dwarf. In this case, we had degeneracy in the modeling that allowed it to be fit by both stellar binary and a planet. And the following Keck observations show a separation that's consistent only with the stellar binary. And so this reduced the planet count in the Suzuki sample from 30 to 29. Okay, this is the same one, but it is just more or less. And so then this shows the summary of where all the mass measurements are. Some of these are from microlensing parallax only. And so this event has a degeneracy in 2 different microlensing parallax models. This one has another degeneracy. This is the one that Katie's going to talk about. And this degeneracy has to do with additional features having to do with orbital motion and compared to the source. One difficulty is shown here. This is a plot from that event, but not showing all the data. This is the constraint from the angular Einstein radius and constraint from the Keck measurements. And for M dwarfs in the disk, you can get this period where these curves lie on top of each other, which makes it hard to pinpoint the location and actually the mass and the distance of the system. So we want to make sure that we plan our Roman observations to avoid that in this result. Yeah, so this is the event that Katie's going to mention. So this is what the event looks like. Because of orbital motion and comparing to the source, we get two solutions with different parallaxes that give different results. We lens detection at shorter wavelengths. Okay, so this is a list of the events that we measured masses for. So there's 28 events with 29 planets, and we have masses for 17 of those. But most of these, actually, the analysis done for the discovery paper is not adequate to explain, to actually get the correct masses. And one of the reasons for that is that when events are being discovered, and typically the sort of higher order effects having to do with maybe a companion to the host star or orbital motion of the planet, they're usually not included in the modeling if you can't really measure measure those parameters very well. But that doesn't mean that they're not important. And sometimes by ignoring some of these things, then you artificially reduce the uncertainty in your measurements. But to get them correct, you have to consider all the effects that could influence your mass measurements. And so this can become more make the analysis a little bit more complicated. All right. So this shows that same plot from Suzuki et al. 2016, showing this mass ratio function where there's a change in the slope here. It's actually not super significant, but marginally significant with the base factor a bit over 20, I think. But there is a peak around sort of a Neptune mass. And now here's the model we fit. So the model includes more than just this 2 dimensions. It also has a separation dependence. The parameter b here, so it's sort of a half plus or minus a half, so it's not super significant, but there seems to be some favor of hosts that are at wider separation than prime sensitivity for microlensing. But with the mass measurements, we now add a couple more parameters. One is the mass of the host star, okay, or the mass, and this is a little bit different than when analysis and radio velocity surveys, when they talk about the dependence on the mass of the host star, they usually consider it as a function of the planet mass. But here we consider it as a function of the mass ratio. And so we find actually a power law here of about 1, so that for the planets that can be found by microlensing, they're more likely, for a fixed mass ratio, they're more likely to be hosted by a more massive planet, by 1 power of that planet mass. Also, we have to include another parameter because we have one event that can be explained by a main sequence host. We include a factor here of the fraction of white dwarfs, and to do this right, you need to include. Since we know something about the mass distribution of white dwarfs and main sequence stars, we want to include the ratio of the priors here. If we were including in the same term along with the main sequence sources that are covered by 1 here. And here we find a fraction of white dwarfs is about 0.36 plus or minus 0.28. So it's, it's maybe around a third with only one detection. We don't have very high significance there, but also we don't measure masses for all the planets, and so some of the other ones could be white dwarfs as well. Yeah, so we can also compare this to radial velocity results, and so I'm taking this from Fulton et al. Because they give the well, I couldn't do it for the Mayor et al. Paper because they didn't publish enough of their data. But here, we fit a similar model and we cut the California Legacy Survey sample to separations between 1.5 and 6 AU to roughly correspond with microlensing sensitivity. We get a very similar power law for basically favoring the sort of Neptune mass planets. So they, well, with this new analysis, including the host mass dependence, we get a minus 0.82 slope, and here they're minus 0.6, but it's consistent with the same slope. And also this power law for the host mass dependence as a function for a fixed planet mass ratio is also very similar. Okay. And then, so to explain, so this number that we got for, for the fraction of white dwarfs, to explain what that means, this is the, 36% plus or minus 28%, for when we see a planet of a given mass ratio, it's the probability that's likely to be caused by a white dwarf, is proportional to this, but it's proportional to this times the ratio of the priors. And this isn't exactly the prior that we used in this analysis, but this is one published earlier by Gould. And so you see actually for masses near the peak of the white dwarf distribution, most of the objects in the galaxy of that mass are white dwarfs. With this mass rate, this mass function, it's actually a factor of 3. And so for a planet, if a microplanet has a 6.6 solar mass host, the odds are about 50% with a large uncertainty that the host is a white dwarf. And so for events where we determine a mass of 0.6 solar masses from microlensing parallax, there's a good chance that the host could be a white dwarf. All right, so actually I had a few slides I wanted to, that actually refer to the next talk by Wencheng Zhang, and I'm a co-author on that paper, so I have some idea what he's going to talk about. And so this is just to compare it. So Wencheng, he's going to report on the KMTNet analysis of the mass ratio function, which, like the Suzuki et al., does not find a deficit of planets where it was predicted between the mass ratio of Saturn or of basically sub-Saturn mass planets, whose mass ratios sort of Saturn or smaller. But they do see a somewhat smaller deficit than predicted at larger mass ratios, which would be a Jupiter-Saturn mass ratio desert, or in terms of masses, it would be Saturn mass ratio. So here is my analysis of this earlier Mayor et al. Sample, trying to look for any kind of dip in the distribution, and these grayscale curves are basically the variation in MCMC models, and then the model has a Gaussian desert, and so the best fit model all finds a little desert here, but it's not significant. And then this is basically a comparison to this California Legacy Survey It also shows a large value at this mass ratio between that of Saturn and Jupiter. And then there's a similar paper, a similar plot in the Fulton et al. This is based on 63 planets at this 1 to 5 AU. And so this should show no evidence for any deficit there, although should show that. Yeah, so it's not the same sample that Wei Cheng is going to talk about, so it doesn't mean there's any sort of conflict, but the radial velocities don't show that. So I can end here and take questions, and then you can get some Wei Cheng.
Wei Cheng, did you want to answer your question? Or ask a question?
Okay. Actually, I have one question and one comment. First, for the radial velocity result, I think it is consistent with the Camden net mass ratio function there, because the host star for the radial velocity study are mainly the G dwarf. So if you go back to the radial velocity slide, you will see, I think is the deeper for the radial velocity study should go to the lower beam. It is 10 to the minus 4 to 3 10 to the minus 4. So it is actually consistent with the Camden result, as I already showed you in our emails. Because the host star are different, right?
Well, so the plot on the right that shows, that's the mass ratio. And that's what you are analyzing. The Fulton sample does include more lower mass stars than the Mayor et al. Sample, but yeah, so I'm not saying that they're inconsistent, but I think there's no evidence for any deficit here.
Okay.
These aren't fully detected efficiency corrected.